If you push a ball, it goes in a straight line. In theory, that should make golf quite an easy game. If you push a door though, it turns around an angle because of its hinges. Now in actual fact, things are often turning around in angles. Drop a pencil, it goes in a straight line. Drop a hammer and it's going to turn. It's all because of moments, and that's what we're going to look at in this lesson video. We want to be able to describe these turning forces well. And the basics are quite simple with this formula, m equals Fd, being the only one we are worried about. M is the moment, the turning effect of the force. F is the force, which is a vector with a direction, remember? And d is the perpendicular distance from the line of the force to the pivot. Okay, you might not have come across that before. I'm saying the line of force because it is best to draw the force like this as a long line. It doesn't matter where the arrow starts or ends. The pivot is over here. So we draw a line from the pivot to the line of force that is perpendicular to the line of the force. So m equals Fd, and F is measured in newtons, D is measured in meters or centimeters. So m is in Newton meters or Newton centimeters. Let's look at some calculations. The box on the right has a weight of 2 newtons and it is 0.4 meters from the pivot. So its moment is 2 times 0.4 equals 0.8 Newton meters. It has a direction too, which is clockwise. Since we're talking about turning effects here, let's try to avoid saying it's acting up or down. Stick to clockwise and anti-clockwise. This mouse, weighing just 3 newtons, is 0.5 meters from the pivot on the left. So its moment is 3 times 0.4 equals 1.2 Newton meters, anti-clockwise. In this one, I have a helium-filled balloon on the left. Its upward force is 0.5 newtons and it is 0.8 meters from the pivot. So its moment is 0.5 times 0.8 equals 0.4 Newton meters. The force is acting upwards. It's on the left hand side of the pivot, so the moment is clockwise. If I put them all together in one diagram, we can add up the moments. Anti-clockwise is just the one at 1.2 Newton meters. Clockwise, we have both the box at 0.8 Newton meters and the balloon at 0.4 Newton meters, making a total of 1.2 Newton meters clockwise. Since the total clockwise moment is equal to the total anti-clockwise moment, the beam is in equilibrium. To truly be in equilibrium, we need to check the linear forces as well. The box and the mouse act downwards with 2 plus 3 equals 5 newtons, and the balloon acts up with 0.5 newtons. That makes the total force from these 4.5 newtons downwards. It doesn't move down because we've got a pivot as well exerting an upward force. And we just worked out that this must be 4.5 newtons upwards because we know it's not moving down. That makes everything in equilibrium. The overall resultant force is 0. So that's an overview of moments. We actually looked at linear forces and we looked at turning forces and how we use the equation m equals Fd to calculate the moment as being the force multiplied by the perpendicular distance. We also saw that we should be talking about turning forces in terms of clockwise and anti-clockwise because they are turning. And that just because something is on the left-hand side of the pivot doesn't necessarily mean that it's going to have an anti-clockwise moment. So there's not a lot to work on here, but you do need to be careful and you need to pay attention to the details so that you get it right every time.